पीछे जो काउंट है वो आगे लेके आना है। Is somebody? तू यहाँ बैठे? नहीं बैठे। There is a bench. पीछे वो bench आगे। नहीं गलत नाम नहीं लिखना, नहीं तो तुम्हें एक्सेंट ना करो।
Okay, please settle down. Start.
A warm afternoon to each one of you present here. It is my pleasure to welcome you all to the day 3 of the flagship event of Physics Society 29th Annual Popli Memorial Lecture Series. Over the past 2 days, we've had the opportunity to gain insights into the subjects of superconductivity and biophysics. And today, we continue the series with yet another lecture. I would like to reintroduce our guest speaker of this evening, Professor Gautam I, Menon, who is currently a professor of physics and biology at Ashoka University and considered to be one of the most influential academics in government worldwide. We are truly fortunate to have you with us. Without further delay, I would like to invite Professor Menon to begin with today's lecture, and I kindly request all of you to please switch off your phones to ensure that the lecture moves smoothly.
Thank you. So this is the last semester of 3 lectures. Wonderful occasion. As I said, Dr. Popli was my own teacher. I think we realized the value of our teachers only somewhat later. I mean, the influence that they have had in making us what we are. And I think my own teachers achieved several decades ago had an effect on me that really lasted for a very long time. In fact, I think my real knowledge of mathematical physics comes from what I learned in school, not what I learned after. is the teaching of that. In fact, the syllabus of that course would actually equal to anything that you might get anywhere else. I hope it's still there, largely. I've never forgotten that after all these years. Okay, can you hear me clearly at the back? So this lecture is about something completely different. It's about how one thinks about infectious diseases. And when I was a student, or even when I was doing my PhD in completely different areas, conductivity and so, I had no idea that 20 or 30 years later, I would be thinking about problems that had to do with these blood vessels. And part of that was also the reason that as a theoretical physicist, I felt I should give a little more usefulness to society.
Maybe
just close it like that, but maybe over there we can.
why don't you adjust it from there?
Just slightly from here.
I don't know how to do it. It's not volume, it's the...
No.
It's not the volume, it's
Hello.
some other thing. It's
Hello. 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 Okay? Yeah. There's a bit of the reverberations when I get up. As I said, one reason for thinking about infectious diseases was the idea that the infectious should be of some larger use to society. And the method that we are trained Hello. Slightly lower. Yeah, that should be fine. Okay, I hope this is now a significant improvement on what it was earlier. As I said, the idea was for a theoretical physicist to give some larger use to society in terms of what they did. And the training that a theoretical physicist gets in terms of being able to write down equations, in terms of being able to write down computer simulations, understanding circuits, that's a transferable skill. You can use it in high finance. So for many years, Wall Street would hire the best physicists out of Harvard, for instance, in order to get them to make money on Wall Street. But I wanted to do something a little less financial, a little more useful in a larger sense in society. So I began to think about problems in disease modeling. Also, the idea was that India is somewhat underserved in people who think theoretically or in terms of models about public health. And that's certainly one of the largest questions that confront India nowadays. For example, we have the largest proportion of children who are born stunted than anywhere else in the world. We have among the largest fraction of diabetics anywhere else in the world. If you look country-wise at estimates of the number of people who died in COVID-19 pandemic, India is larger than any other country. Of course, we also have a large population, so even a small percentage of that large population is a large number. But that certainly points to remember all of the people who died as a father, a brother, a mother, a sister, or somebody. So there is a very personal way in which infectious diseases such as COVID, that's not the only example, affect all of us. So what I want to do is to explain a little bit about how one thinks about models for disease, and then from there to go to the question of what is it that we can do that is different and unusual, and in a sense, better, more targeted towards India than other types of methods. So the whole field of disease modeling is a very old field. In fact, it goes back to famous mathematicians Bernoulli, Hamer, and other people who began to work in the 1700s, 1800s, etc. But many of the ideas behind this are actually older ideas. In fact, they go back even to thinkers, great Arab thinkers, the 1200s and so on, who first figured out why was it necessary to quarantine people who came in exhibiting symptoms of a disease. So the idea when you had ships coming into ports and there were reports of any disease on the ships were asked to stay outside for 40 days. Quarantine really comes from the word 40. So that people who were diseased could either die or recover from the disease at that time before they began to contact people on shore. And so that's a background that comes from earlier. But the real breakthrough, in a sense, comes from the idea of the germ theory of disease. And that says that infectious diseases, diseases that pass from person to person, are diseases that are carried by some very small microorganisms. Right now we think of this as completely natural. That the tuberculosis bacillus, there is the COVID-19 virus of SARS-CoV-2, there were other viruses earlier, there is the flu virus and so on. But the whole idea that something could pass from person to person in order to transmit the disease, and that something was very small, only visible under a microscope, and in the case of viruses, not even visible under a microscope, but had to be inferred through other types of techniques. That was an extremely important idea. If you look at the history of ideas overall in science, along with the idea of relativity, the idea that the speed of light is constant in all inertial frames, that it could convert between mass and energy in a particular way, the theory of evolution, the fact that everything is made up of cells, the cell theory. The germ theory of disease is certainly one of those ideas, because in the sense it has been the most impactful. And to think about this at a time when people didn't even know that germs existed at all, that anything microscopic really existed, and could potentially be a carrier of disease, and could then be identified, was a very important idea in terms of the evolution of intellectual ideas overall, the intellectual history of science in a certain sense. Then the big name after this is, of course, there are a bunch of names all associated with India who worked in India at some point. And certainly one most important name is Ronald Ross. So Ronald Ross got a Nobel Prize in medicine / biology for the discovery of the malarial parasite, the life cycle of the malarial parasite, and figured out that malaria was transmitted from human being to human being through an intermediate vector, the mosquito, the Anopheles mosquito, the female Anopheles mosquito. And what carried it was a very small malarial parasite, which was responsible for moving. It had a life cycle within the mosquito, it had a life cycle within the human being. So that was Ross's contribution to malaria, which was an experimental contribution, an epidemiological contribution. But Ross was also a mathematician. Ross also worked out a set of equations that we now call the Ross model. They describe how malaria moves from person to person. He used to write down an equation for the mosquito, what happens to the mosquito, and an equation for what happens to the human being. And he tried to identify public health strategies. For example, removing mosquitoes in a particular area, mosquito control as a way of holding back an epidemic of malaria. He goes to the early ideas of Mr. Ross. Okay? So Ross was doing his work in 1895, 1905, etc. He got a Nobel Prize somewhere around that time. And then his mathematical ideas were influential to some extent. But the really big breakthrough came from two people. One is called Kermack, and the other was called McKendrick. Both are very interesting stories. McKendrick and Ross were both part of the Indian Medical Service. They were sent out from the UK, from Britain, to India in order to attend to the health of the European population, but also to some extent the local native population, and investigate tropical diseases. But the whole idea of tropical diseases was very important at that time, because they felt that this was a new way of understanding new diseases. The London School of Hygiene and Tropical Medicine takes its name from this old sort of semi-imperialist way of thinking about the tropics, people who stay in the tropics, the diseases that people there are subject to. So Mr. McKendrick was also a person who was sent out. He, in fact, headed, I think, the Pasteur Institute at Kasoli was headed by him. He spent many years in India, and then he went back to Edinburgh, where he headed a prominent lab in Edinburgh. Kermack, as far as I know, never visited India, but he was an unusual person. He was trained as a chemist, but had a lot of mathematical ability. One day, when he was fairly young, he was said he was working on a chemistry experiment, when it blew up in his face. He was instantly blinded, and thereafter lost his sight completely. So what's a person to do? You cannot be a chemist. A blind chemist is a somewhat difficult thing. You could be a purely theoretical chemist, but to do anything experimental while being blind is a much more difficult proposition. So he shifted to his initial first love, which was mathematics. So apparently he was so good at mathematics They could imagine the equations in his head. He could work out entire calculations in his head, and finally someone would have to write it down for him. So Kermack and Mechanistic were, in a sense, very central figures in our modern understanding of disease. And it was an interesting combination between someone who had actually been trained as a doctor, worked in India, and then come back and do the whole spectrum of tropical diseases. He was very interested in plague. There was a plague epidemic in Bombay around 1904, 1905. And that's the epidemic that Mechanistic knew very well. Together with Kermack, who was a great mathematician, who could probably think all of these things in his head, they began to analyze and look at the old data that existed about the plague. So one example of that, of the sort of data that they looked at, would be something like the number of cases or number of infections as a function of time. And we would sort of generate a curve that looked like this, and here was the sort of data. And the numbers here would be something like 500, 1,000, 1,500, etc. This is a very standard look of what's called an epidemic curve. The number of people infected as a function of time starts off small, rises to a large number, and then comes down. If you remember, during COVID-19, much of the discussion was actually about curves like this, when is it going to turn around, when are the number of cases going to come down, etc. But all of that analysis owes to early thinking about the shapes of these curves and how one understands the shape of these curves. Okay, and when Kermack and Mechanistic worked out their theory, they were looking at data that were essentially these data points, and they managed to figure out a mathematical expression that they could derive exactly fit those points. And so that gave people working in the area of mathematical control of disease, mathematical modeling of diseases, some sort of positive feeling that, look, maybe these ideas are in fact generic and important enough that we can use them as a basis to think about disease. Okay? So let's just look at the sort of models that one can write down, very simple models that one can write down. And to do that, we have to think about how people contract diseases. So we've established that people get diseases from each other, that someone who's infected by the disease can infect you if you are not already infected. And that's the basis of the germ theory of disease. But let's just think about populations in general and say that, look, populations consist of people who are susceptible to the disease. So let's just write that as S. Okay? If you haven't had the disease yet, you are susceptible to the disease. The second category is people who are infected. And we can sometimes also call this infectious. And the third category is people who are recovered. Okay? 3 categories. So they're susceptible, infected, and recovered. If susceptible, maybe there are 500,000 people in the city who are susceptible to that. Maybe there are 20 people who are infected. And maybe there are no one who's recovered right at the start of the epidemic because no one got it yet. If you add these numbers up, that should be the total number in the population. Okay? What we've done is we've mathematically said that, look, we're going to put each person into a particular box. The box may contain susceptible people, it may contain infected people, or it may contain recovered people. So this is the idea behind what are called compartmental models. And the model says, here's a box, a compartment for the S people, here's the box or a compartment for the I people, here's the box for all the people who are recovered. So the rules are, you know what the rules are. That if you're susceptible, you can become infected. That's like taking a person or a group of persons from here and putting them in this box. Or you can take, if you're infected, you can recover. So that's like taking a bunch of people from here and go there. Depending upon the disease, suppose you die from the disease that this R is also used for removed. Essentially, it's subtract from the population. But that's just a technical thing. Normally, this is probably more reasonable to just call it recovered or just R. This is the famous model called SIR model. In a sense, it's the simplest model for an interesting disease that involves these two things together. So you should think of these as compartments. That's why it's called a compartmental model. Each compartment has a certain number of people, the number of susceptible, number of infected, number of recovered. And if everybody is in one of these categories, S plus I plus R must equal the total number N within the population. That's the basic idea behind model synthesis. There's one more idea, which is of course that you cannot automatically suddenly go from S to I, because we know from the germ theory of disease that you need to contact someone with the disease, so this class of disease, in order to be infected. So that's often represented as an influence, which is a dotted line that connects the I to S. This says the I influences the number of S by taking those S's, infecting them, and moving them to the I compartment. So that is the logic that one would actually apply here to think about the problem. There are simpler versions of this. For example, there are no recovered states. If everybody finally gets infected, you just go from susceptible to infected at some rate. Okay? And you can also put in additional compartments. You can go from susceptible compartment to a compartment called exposed compartment. And in the exposed compartment, you have virus in you or bacteria in you that's slowly increasing in number, they're multiplying inside your body, but you haven't reached the threshold where you become infectious to other people yet. You can go from S to E to the exposed compartment, to the infectious compartment, to the recovered compartment here. Okay? Okay, depending upon the disease, each disease carries with it some model that is appropriate to that disease. And you often, there are sort of subtleties in deciding what is the right model to use that are not completely apparent. And that's the role of the epidemiologist, the person who goes out into the field person, who looks and says, what are the peculiarities of the disease? How are people getting it from each other? And I can tell you from a particularly grisly sort of compartmental model. That's in the case of Ebola. You've heard about the word Ebola, you've probably heard about the disease at some point. Ebola is a disease that transmits, that is has very high fatality. About 80% chance that you will die if you're exposed to Ebola, so it's not a good thing to consider getting. It also transmits through close contact of bodily fluids. So for example, if you're in close physical contact with someone with Ebola, if you're sharing a towel or sharing some sort of fluid or holding his body, etc., then you are much more likely to contact the disease. So a lot of Ebola has been sort of with us. The earliest reports of Ebola was in the mid-70s. And periodically in Central Africa, you would hear of outbreaks of Ebola, and immediately the WHO sends in teams in there. But already West Africa's response to outbreaks of Ebola is very, very strong. They're very strong public health system that targets that particular disease. So typically it gets controlled after a while. The peculiarity with Ebola is the discovery that burial practices also had a role in infecting people. The traditional burial practice of Ebola patients, of anyone who died in Africa, is to bathe the body, to clean the body while you are actually in contact, and the fluids that are released as a result of that bathing could potentially be infectious. So you need to have additional compartments because even if you are recovered/removed, it could actually be infectious. That's an interesting sort of peculiarity, which is a bit sort of depressing if you think about it. But it also tells you how important it is to understand the behavior of the disease before you begin to write all of these models. So right now, I call it a model, but it's just a little set of boxes here. There's no real, as yet there is no mathematics, there is no science inside this at all. And so the next step, of course, is to write down equations that tell you how it is actually behaving. What we want to do would be to write down an equation here. This is how S changes with time. This is how I changes with time. This is how R changes with time. Okay? That is the creation of a model from a picture. Some sort of picture that we will actually write something. So what would we write down over here? First of all, susceptible people must come into contact with infected people in order to become infected themselves. As you're infected, you leave the susceptible compartment. You deplete the susceptible compartment of numbers. So this rate must have a negative sign for that reason. Must be proportional to the number of susceptibles and the number of infected, again for that reason. And for technical reasons, we will divide by the number here, the entire population. And that's for a specific technical reason that these models are written down. We won't worry about that. And then there must be some number that tells you the rate at which you actually get infected. That I will call it beta. Okay? So the logic is that this changes, this decreases, because susceptible and infected come into contact with each other, and the rate at which that happens is this beta, which is something like the infectivity how efficiently can you infect someone and then move them from S to R. Okay, so now we have extracted people from the susceptible compartment and moved them to the infectious compartment. So whatever you take out of this box must come into the second box. So there must be a contributory term which is a plus sign and everything else, beta Si divided by n, then n plus n. Because everything that is left here, which is this term, the minus sign, must be added on here, which is this term, the plus. So now we figured out how to go from S to I. Now, how to leave the I compartment? You leave the I compartment when you recover, and so you would put a minus gamma times I. So minus because you're leaving the compartment I, and of course it depends upon the number of I, and gamma is the rate at which that happens. Okay? First equation, second equation. Third equation, how does the number of R change? Well, the number of R changes only because people who left the infected compartment can come to this compartment. So there must be a plus and a gamma times I. This set of equations is called the equation for the SIR model. And this has two rates, one is beta, one is gamma. I call this a rate because this is a number, this is a number, this is a number, this is a number. This is 1 over time is over here. So beta must have the dimension of 1 over time, therefore it is a rate. And the same holds for gamma. You should get comfortable with these sort of arguments about what is the dimension of this, what is the dimension of that. So they're actually very useful when you think about this. Okay? So now I've already told you a lot of intricate mathematics just in this. We have written down explicitly the equations that govern the SIR model. And they take particularly simple form. There are many interesting approximations that are made here. One approximation is that everyone here is in principle contacting everyone here at some rate. So it doesn't take into account the fact that if I have a city that sits like this, people here are primarily contacting people here are primarily contacting people here. So this sort of spatial variation, the fact that different things can happen in different parts of time. What is happening in Saket is not the same as what is happening in the new campus, etc. That's not there in these models. So these are what are called mean field models, but this particular name doesn't really matter very much. I'm just telling you that this is an approximation that is made. Little things about this. Alright? So now one has equations, what does one do with these equations? One thing that one does with these equations is to ask the question, if there is one infected person in the population, everybody else is, everybody in this room is susceptible, let us say. But now some new disease is coming along, and the person in the blue shirt in the third row is the one person who is infected. How many people does that person infect? What is the later course of the disease? Does it go up in this way? Does it go up like this? Does it go up like this? Or in fact, does it just basically come down right away? So that's the distinction between something that is an epidemic and something that is not an epidemic. In an epidemic, the number of cases grows and grows and grows until finally some finite fraction of the population, 10%, 15%, 20%, are infected, and then the curve begins to come down. If it's not going to be an epidemic, you can infect a few people, but that number comes down. It never reaches a finite fraction of the population. Some number will be infected, but never a number that is a significant part of that population itself. So how do we think about that? Well, one way is to ask exactly that question. Suppose the whole population is there about to potentially become infected. I put one person in there and ask what is the consequence of that. For that I can say, look, I is basically small. Okay, there is one more thing that I must do before I get to that point. That is a very small sort of modification of these equations. That is to say, instead of counting S plus I plus R equal to N, let me just work with the fraction S equal to I divided by N. No, sorry, small s equal to capital S divided by N. Small I is capital I divided by N. And small r is capital R divided by N. And they're writing it as a fraction. So now instead of adding up to N, they will add up to 1. That doesn't affect anything really. It's just a way of writing these equations. The great advantage is that I can get rid of these factors of N that sit here. And then my final equations are d small s by dt equal to minus beta small s and small I. di by dt is plus beta small s small I minus gamma small I. And dr by dt is plus gamma small I. Sorry, I'm writing this somewhat badly and doing it very fast to show you. But all I'm doing is just dividing by n and sorting out the fact so that the n here vanishes. You don't have to worry about that anymore. So now we're going to ask this question again. What happens if there are many susceptible people and one or two infected people? In that case, I can say that my small f is approximately equal to 1. My small I is very small, close to 0. Let me just call it epsilon here. And R, of course, no one has recovered yet. We want to ask what happens. So let me look at these equations in that approximation. Let me look at this particular equation right here. Okay? So if I have something, take this equation, I have d epsilon by dt is epsilon times beta minus gamma times epsilon, because s is approximately 1, I take it to be 1, and the I is very small, which is the epsilon. So an equation that looks like that. It's my simplified equation. It's only true right at the beginning, when s is the larger number, and epsilon is really, really, really small, a fraction of the total population. This is, of course, beta minus gamma times epsilon. And now you can see that what happens depends upon the sign of beta minus gamma. If beta minus gamma is positive, oops, it goes up. If beta minus gamma is negative, this comes down. So whether you have an epidemic or not, whether you see a number of cases steadily rising, depends upon the sign of beta and gamma. Alright? So beta minus gamma should be greater than 0 for the pandemic, or beta greater than gamma, or beta divided by gamma greater than 1. That's another way. This combination is called the basic reproductive ratio, and it's the most important thing to know about a pandemic or any disease. If the basic reproductive ratio for the disease is larger than 1, the epidemic will really set in. It will sort of slowly grow and grow and grow until larger, 5%, 10%, 20%, 50% of the population will actually be infected. If it's less than 1, I see 20 cases today, should I be worried? No, because I know that tomorrow, day after, etc. If it will go up a little bit by randomly, but it's finally guaranteed to come. I will never have 10,000 people infected, starting with 20, provided the reproductive ratio is less than 1. So already this is the actual one.
So in giving small I by dt, I guess there is a minus gamma I and
Yes, did I make a mistake here? This is plus, this is this opposite sign here. I removed the factor of n.
the next one
We divide throughout by n.
Where?
Addition, minus gamma and minus
There
gamma.
won't be n. That's basically removed because this and this must have the same dimension. If I make the change of variables here,
So it's
n
n
is
square.
approximately 1
It's n
That's
square.
okay. No, that's okay because you divide by n both sides so that capital S becomes small s. That's all right. That's all right.
Work it out. That's all I can say. It's the easiest way to
No,
sort of.
the only term in the second equation that gets an n is s by n. Rest all is capital
Yeah,
S, so it can be
so
easy.
exactly. So there's an n on top of this, and that cancels. So that you really want to remove this. Otherwise, you divide by n, you get it. There are no more further factors around that equation. Okay. So this is the basic reproductive ratio, which is the core of everything that we actually want to understand about the disease. And therefore, whenever any new disease comes, whenever COVID-19 came, remember that COVID-19 was first detected in late 2019 in Wuhan province in China. In the city of Wuhan, the province of Hebei in China, between about the 15th of December and the end of December, there was a sudden rise of cases of the disease. It seemed like pneumonia, but it wasn't actually pneumonia. It was not any standard pneumonia that we knew about it. People began to die. And then by early January, by the late December, early January, people had figured out this is a new disease. We have not seen it before. And then between the month of January, month of February, month of March, but as the disease spread between China to South Asia to Italy and then to other parts of the world, a huge amount of effort of epidemiology went into figuring out what is the basic reproductive ratio, what is this number that tells you how fast it's growing. And because you're beginning with a small number of cases, you're dealing with maybe 100, 200, 300 cases, to believe that R0 was somewhere between 2 or 3. That number in some cases became larger, in some cases became smaller, until finally narrowed down somewhere between 2 and 2.5, which is our current understanding of that initial variant of COVID-19. Of course, later variants were transmissible, more transmissible, therefore they had a larger beta, and the R0 value got pushed up. For example, the R0 for Delta was probably closer to 4 than to 2 or 2.5. But already you have now seen the most fundamental description in terms of mathematics for what is involved in thinking about a disease. The first thing that anyone in public health actually looks at is what is the reproductive ratio for that particular disease? What is the interval between cases? How long does it take to infect somebody? How long does it take for people to recover? Are there people, do they more or less recover in 4 to 5 days, or do some people take weeks to recover? And therefore, do they remain infectious to other people during that period? Okay? Alright, so that's one thing. So, these equations, interestingly, cannot be solved exactly. You can't write down a closed form expression in terms of standard functions of these, even though they look very, very, very easy. That's because this is a non-linear term. Everything else is linear. So the product of S and I become non-linear. So there are only certain approximations you hope to solve it. You can certainly solve it numerically using MATLAB or Python or whatever it is. So the usual way to do it is to solve it numerically and ask for this. And you can make much more complicated models, as I said, putting an E compartment, putting a vaccinated compartment, putting other types of complicated compartments that are appropriate to a specific disease in order to improve our understanding about that. So this is, as I said, these are compartmental models of disease, and they are the most basic models with which to think about disease. I said most basic. So how, in what way could we actually improve these models? One way is to say that, look, these models make very specific assumptions about how people contact each other. And I mentioned that these are called mean field models because in principle, within the situation described by these models, anybody can contact anybody else. Then I said that that's not really the situation in real life because I contact people in my particular neighborhood, I contact my family, I contact people at work, etc. But a completely arbitrary person on the sitting somewhere else in some other part of the day, I'm very, very unlikely to come into contact with. So that's certainly an assumption that is incorrect. How do we improve on that assumption? So one way to do this is to think about networks of interaction. And when you think about networks, you're saying here is an individual here, this individual is contacting so many people here, etc. They have their own set of contacts. The nature of these contacts can be complicated. You can have people who contact people like this. You can have triangles of contacts, etc. So this is a network. You can draw many different types of networks. If I told you about this network, then you would say, okay, if this person is now infected, the only person he can infect of this susceptible lot are all the people he's connected to by network. These are physical networks of interaction. It's not counted if I talk to somebody on the phone. I'm still connected to them. I have to be close in proximity to them in order to give them the disease. If I have access to network, that includes the possibility that now I have different spatial regions that now I can think about. Say, people over here interact with each other, people over there interact with each other. I'm connected to my cousin who I see once a week, so that's another interaction that I might have. So it's just not just local in space, although much of it is local in space, it also allows you to contact people from far away. That's one improvement that you can make. So actually thinking about disease spread on networks. Yeah.
You actually use this, you initially have a lot of information about the network. Supposing I make kind of a surmise that my beta beta depends on my physical situation. Say exponentially goes down and I do an analysis. Would I be terribly wrong?
It depends on the sort of disease situation that you're considering, the nature of the population, etc.
Yes,
So there are many variants that you can do. In a sense, that is a sort of network where you say that it's a network embedded in a sort of physical space, and the way I'm going to construct that network is I'm going to favor connections that are close to me in physical proximity and proceed on that basis. What I'm going to tell you about is something like that, but one step ahead. So give me a little more time and I will explore that.
I was just worried that to actually use this, you need to know a lot about these.
That's absolutely true. In order, so here you didn't need to know anything. All you need to know is what is beta and what is gamma, in a sense. But over here, I have to say about what is the nature of the network, how people are connected, etc. One way is to say that I just make synthetic networks. I have some ideas of social interaction between people, what those networks look like. If I'm really clever, what I will do is, for example, study a school, for example, I'll put little electronic tags on all the students in the school, and these tags will pick up whenever two students come close to each other. And then I can make a network like this. So that's way they've done. But in general, in a population, it's very hard to do. So people usually make a guess at the sort of networks that are there based on some sort of social organization. So that's one set of models that people use to study disease, and there are a bunch of results associated with those models. Much of this has to do with the peculiarities, the many different types of networks it is. It could be random networks, it could be what's called small world networks, etc. Many different types of network structures that are embedded in this. But all of this, in a sense, is an assumption about how people interact and the way they interact. And that assumption may or may not be accurate enough. Nevertheless, at some level, it's an improvement on these earlier models, which is to everybody interact with everybody else. The models that I'm interested in are a different category of models, and they're called agent-based models. I want to tell you about, so now I will, in the last 10, 15 minutes, I'll tell you a little bit about my own work in this, and motivated from thinking about agent-based models. So the reason to think about agent-based models is, first of all, our ability to simulate things is now much better than it was 20 or 30 years ago, and certainly very much better than it was when these people wrote down their equations. So now I can say that I can actually simulate people in the population. And I can simulate 1 million people, 10 million people, 20 million people as individuals within that population. Okay? So the idea behind an agent is to simulate every individual. So what does that mean? And how is that actually going to be done? But the idea is that if I suppose I took this room has approximately around, let's say, 40, 50 people inside it. I define an agent for each one of you. Each of these agents is not exactly the same as any other agent. For example, some of you are male agents, some of you are female agents. Some of you are aged between, let's say, 20 and 30, some of you are aged between 50 and 60, etc., etc. And that age makes a difference because, for example, you were both infected by COVID. The older person is a little more risk of being hospitalized than a younger person. So there's obviously a difference there. So I must tell you about the gender of the person. I must tell you about the age of the person. People who are diabetic, for example, are a little more at risk of something adverse and for bad consequences than people who are not diabetic. I must also tell you about who is diabetic in this particular population. I must also say where do you work, where do you stay. If you stay in a place that is a hotbed of COVID-19 cases, when you come here, potentially you're likely to infect people over here. Your geographical location is also important. Who are you talking to? If you don't get along with them on the side at all, then you are unlikely to meet each other, you're unlikely to contact each other. It's your friends and the people who you talk to on a daily basis who you're more likely to infect. Even there is the idea behind the network, but that network is in a sense a network of physical interaction that is embedded in the description of an agent. So an agent has a lot of information inside the description of an agent. You can say that each agent is like a little box that says this is the age of the agent, this is the age, this is the gender of the agent, this is any pre-existing conditions, this is the home, this is work. And then I can add more to these things. For example, I could add economic status. I could even add social status. And so on and so forth. And I could make as long a list as I wanted. And I might make a list with something like 200 items to be specified in my description of an agent. Okay? The problem is one of privacy. I can come and ask you, tell me what your age is, tell me what your gender, tell me what your description, etc., etc. But then I have very personal information about you that you might not want to reveal. You might not want to reveal this because big companies, for example, like insurance companies, can be very alert to potential issues with you and say that, look, I don't want to give you insurance because you have diabetes, we didn't tell you that earlier, you have this condition, your parents died early of some disease, therefore you are more likely to get it. From my point of view, you are at risk. You are at greater risk if I were to insure you. Then if I was to be assured that you have a very good chance of surviving until age 90 or 95, in which case you would have paid out enough in premium that it doesn't matter, I can cover whatever happens to you at the end of your life. Getting private personal information about people is something that medical people on the clinical and medical side are very careful about. They just don't want to do that because that opens up a whole new Pandora's box of possible bad consequences just arising out of that. So what we need to do is to extract what is called synthetic data in order to make what is called a synthetic population. What that does is that makes on a computer a bunch of agents that represent this population as closely as possible, except the connection between you and the agent is not there anymore. If I look at my agents, on average 50% will be male, 50% will be female, whatever ratio there is inside this particular room. All of you will be studying students together in college X. You will have height and weight given by a certain amount. That is not directly tied to what your is in agent. But if I take the distribution of heights and weights in this class, that I can reproduce in my description of the agent. But actually putting a lot of stuff into the agent, but none of it can be identified or dates back to a particular person. On average, that it could be you, or could be you, could be you, could be you, but it's not exactly you. How do we harm?
So all these features you extract from the empirical institutions, you sample them from?
That's right. So then you must ask where you get this data. From that you take the census of India, you take various surveys for the IHDS survey, you take the gridded population of the world to find out population densities, you do this in order to find out what is the distribution of other characteristics. You can look at other biometric information, distribution of heights, weights, etc.
So they will probabilistically generate.
That's right. You know the distributions of these and you generate the same distribution in your synthetic formula. There's a lot of machine learning that goes into this particular step. It's a fairly complicated step. But once I have a synthetic population of agents, then I can make them do what I want. That's a great idea behind this computer simulation. I can distribute them in my city according to what I know the population density of my city is. I can say that agents travel on average somewhere between 5 and 10 kilometers to go to work and come back. I can say any agent below the age of 18 is going to school and coming back. I can say these are the distribution of school. If I had the actual GIS information, geographical information about the city, I can put in the information about the schools, about the markets, about residential localities, etc. in that and populate my agents. I'm not actually, again, emphasize, I don't have personal information about any of these agents. On average, these agents look exactly like the population that with the real population, if it's constructed on a computer. Now I can take this and I can run it. I can say maybe this agent, so I have my city which is sitting here. Here is my city. I have the population density large here, large here, large here. Maybe I even have sort of rivers inside the city. I have bridges crossing the rivers. All of this I can put into my model. It's not a problem. Maybe my city has something like 3 million people. And that's not a problem from a computational point of view because it has 3 million agents inside here. And once I do this, I can say maybe I infect 5 people here to start off with. As time goes on, more and more people are infected. Because this person has traveled here, I can set off a secondary infection right over here. And I can look at a spatial map of how this is actually spreading. In order to benchmark this, I should know what is happening. I can say that, look, I will only choose out of all possible histories here, those that look like the histories that I've actually seen in real life. For example, if on day 1 there were only cases here, by day 10 there's cases here. There is some history of these agents moving back and forth, infecting other people, that corresponds to that. Then I can ask how it is actually spreading. So that's a much more detailed, microscopic way of understanding disease here. It puts in all of the information, it also puts in very subtle information about society. For example, I said social status here. One problem in India, of course, is the fact that you interact very caste-wise. The way you interact with people is often determined by what caste you belong to, what social strata you belong to, what economic status you have. You can put those details in by favoring certain types of interaction and asking what does this do to disease? How does that change? because then you're able to intervene much better. Economic status, for example, it may happen that people who have to go out in order to feed their children, some of the lowest economic strata, they cannot obey a lockdown, because if they obey the lockdown, they will not be able to feed their family. So they violate the lockdown. Are people who are well off already are well stocked up at home, they have no difficulty dealing with the lockdown for a week or 10 days. But that's not true for all the population. Essential workers must go out, do sanitation, do medical things, are a part of the population that are much more in contact with patients. For example, because someone who visits 20 households in order to clear it up is in contact with each of them. Again, you can put that into the social model. These look very detailed, very complicated, and they are very detailed and complicated. But once you conceptualize it, putting it on a computer is a big job, but nevertheless it's a doable job. And then you can really begin to ask, what happens if I intervene in some way? Suppose I close down all schools. Can I slow down this process of the disease? Suppose I prevent people from traveling from this side to this side by just putting a block on the bridge. Does that change the way the disease is actually spreading? If I prevent any importations into that district, into that city from outside, does that change the way the disease spreads? So that's why I think these ways of thinking about disease spread are very important, because they really illuminate for you what sort of interventions you can make, how these interventions can combine with each other, and how can you construct interventions that disrupt life minimally and yet are powerful enough to hold back the spread of the disease until such point you can get drugs and vaccines into the population. So this model that we have worked on is something called Bharat Sim, and it has a website which I'll encourage you to all look at. We have a bunch of examples of how to use Bharat Sim. Any of you can download Bharat Sim and run it on your own laptop. You can't run it only for 20 million, 30 million, you need a proper computer for that. But on a laptop you can easily run 10,000, 20,000 without a problem and actually see how it works. And this is written in such a way that people who are not necessarily expert in computation can figure out how it's done. There's a bunch of sample programs inside there that actually use this. Bharat Sim is useful and important because it's very specifically tailored to India. We have synthetic population that describe the city of Pune, which we studied in detail, the city of Bombay, and increasingly we are working on getting better population for each of the cities itself. We call it Bharat Sim because we wanted to potentially one day simulate 1.4 billion people. Right now that's very far away. We have to rewrite the whole code in a much faster way for that to happen. But we can do something like between 20 and 50 million on computer simulation, which is still very, very large. The most practical work. That includes the city of Bombay at about 14 to 15 million. The Delhi NCR is somewhat larger at about somewhere between 30 and 40 million for the whole NCR part. But we're sort of getting to that. But more than that, you can actually check by looking at interventions, looking at what's called counterfactual, something that didn't actually happen but could have happened, what those effects and impacts might be. So I wanted to talk about Bharat, but again, as I said, I gave in the last 3 days, I gave you examples of what physicists do. How one physicist went through a certain process of evolution, of thinking about problems that were standard physics problems, in superconductivity and then the role of experiments. What I hope you took away from that first talk was the fact that physics is an experimental science. None of this would have happened if Mr. Meissner had not checked that the field was being excluded from the sample outside. Certainly theory made important breakthrough, but to verify that, it had to take someone who actually sat and did an experiment, put this thing together. If Mr. Cameron Montes had not decided to create the coldest place in the world, we would not have seen superconductivity at all. So the fact of pushing technology, pushing physical limits as much as possible, is very much a feature of what I think is important. But that's something that I hope all of you will remember. The fact that quantum mechanics is a basic substructure and support of everything that happens in physics is another very important thing to remember. The whole of superconductivity is a profoundly quantum mechanical problem on a really macroscopic scale. It's a true macroscopic manifestation of the fact that quantum mechanics actually works, along with all its different implications of the quantization of magnetic flux. These lines of magnetic flux are observable and calculable, and the many experiments that you can use to actually verify what they are. That is talk number one. Talk number two was about a whole new field within physics that has become increasingly popular, which is the field of biophysics. And again, in a sense, that is just as the last century, the 19th century was the century of, in a sense, engineering. And the 20th century was unambiguously the century of physics. Quantum mechanics, general relativity, a whole bunch of other things. Basically, our ability to make materials using physics, to design materials in appropriate ways. The first all of what we understand about astronomy and astrophysics really comes from the explosion of activity over the last century. But this century, if you ask me, will be the century of biology and understanding what goes into life and what constructs life. And that's something that physicists should not stray away from, because we are in a unique position to be able to contribute because of our training, our quantitative abilities, and our interest in things other than the very sort of specific things that we are actually doing. To do that, we have to learn many things. We have to learn some biochemistry, we have to learn about evolution, we have to learn about different types of experiments that are done which to understand biological behavior. We have to work very hard in doing that, but nevertheless, it is very important. My last talk today was about something completely different, as you see. And that was about how physicists can contribute to areas that are very, very far from physics. Actually, biophysics is seeing where physics is applied to biology, where physical principles which are believed to be absolutely correct. Finally, physics should explain everything. That's really what we understand as physicists. But now we're moving into areas where we can use our training and techniques in order to think about things that are very different. This is really, the whole idea behind Bharatam is in a sense the idea behind the Monte Carlo simulation. That some of you may do, some of you may have done already. But this is a huge Monte Carlo simulation with incredible complexity, because you're modeling each agent with 200 different parameters, how they interact with each other, the networks at home, the networks at work, what happens when they go to hospitals, how they move on public transportation. You can put all of this into the detail in which you describe the population, and your computer program can essentially do what you want it to do. And you can answer very specific questions that have to do with how diseases spread. So this is, in a sense, an example of how people trained in physics should be able to think about other types of problems of equal, if not more important, to humankind, in this particular case, infectious diseases. There are, of course, many, many other problems. I'm interested in health personally, because in India, questions of health are very important, are going to be very important in the future. But one can also use these to study social phenomena. That's another interesting direction. People use agent-based models to try and understand how people make economic decisions. How do people respond to rumors, for example? How do I make them invest or not to invest based on the information that I have? That's just a bunch of agents talking to each other, providing information, transferring information from one to the other, and making a decision consequent of that particular information. So with that, let me thank the Department of Physics that let me thank you for this invitation. It's been wonderful to tell you a little bit about what I do. And I owe a debt of gratitude to Mr. Popli, as I said, Dr. Popli, for teaching me at a time when I really needed to be taught anything. Much of what he taught me has stayed with me for the last 40 years. And much of what I told you about really owes, in a very deep and concrete sense, to his teaching. Thank you very much.
Modeling of infectious diseases. And now I give it to the audience to raise their doubts and ask questions.
Thank you for the great talk, sir. Do we have any real life instances where such model building was successful in preventing any disease spread or pandemic spread?
So almost as soon as the disease starts, the modelers are at work. And the modelers are very much in touch with people who make policy. So the decisions of when to lock down, when not to lock down, what to do, how to handle cases, how to check if cases are moving outward, how to administer vaccination. There are many ways in which you can vaccinate people. Vaccinate everybody in the community. Or you can concentrate on what's called ring vaccination. Vaccinate the person closest to the one with the disease, and then work outward in successive ways. You must combine what you do with the model with what is the information that you constantly update based on what you understand from the disease. So there are many examples now. In fact, all of decisions regarding vaccination must come from models. All decisions regarding what you do with dengue, malaria, etc. come from models. So the WHO has very complicated models that address very specific questions about policy. And vaccine modeling is one very important part of that.
So, sir, have they proven successful?
They absolutely have. Of course, the problem is that it's hard to establish a counterfactual. If I had not vaccinated somebody, what would have happened, I don't know. So for that, again, I need a model to say that, so here is the impact of the vaccination problem, here is what it is supposed to do. And I can examine that impact by saying that if I managed to reduce the potential numbers from what they might have been expected to be. So of course, that is evaluating something against something that didn't happen, counterfactual. because it chose to intervene.
Sir, that was in our model which we had been studying, and then we thought of doing some intervention to prevent it. And could we see that it worked that way and didn't go worse?
So the problem is that if you implemented the intervention, then you don't know what will happen without your implementation.
We know from our model which we did.
From the model, but then you must trust the model enough. And that part of that is exactly the process of modeling, connecting the model to data, predicting other types of epidemics, how they behave, to make sure that what you are modeling is correct and people can trust the model. Once you trust the model, then you can ask these sorts of questions in more detail of what sort of interventions work and how well they work.
So in continuation to the way you answered, and he asked success and trust, it really depends upon how you model your agent, right? And the way you're modeling your agent depends upon a lot of parameters that involve dealing with public, in the sense it involves census, maybe circulating a form, taking information from public. There's a lot of thing that can happen at that point. One, the census that you're working on, in countries like ours, how regularly do we take census? In 10 years, situation in India can drastically change.
Yeah.
Right? We are such an evolving, and also, can you actually trust the data that you collect from people? Are people really truthful about giving you the data the whole model depends on that. So if you say that we should trust our model, or if we go by the fact that a model developed by WHO that works in US should work in India or should work in Africa, I mean, is it something?
Or a very good question. So the modelers are very intensely aware of this, of the fact that the modelers only say his predictions are only as good as the data that actually comes in. So, for example, our last census was 2011. We had no census after that. But Niti Aayog has provided some projections for each state, saying starting in 2011, this was the population ought to be in 2019, 2022, etc., etc. So we have some information there. All of these other surveys, the IHDS, etc., are surveys that look at a population of 10,000, 20,000 people, or done to multiple districts, or even within each district. And they ask many questions. It's a very long survey. So among the questions, they may not ask you what is your income, but they may ask you, do you have a refrigerator at home? Do you have other types of appliances? Do you have a two-wheeler? And from that you can reconstruct. Even if you reply, you have to lie very consistently on all of those questions for that to be messed up. And there are many independent checks on these. But for us, for our purposes, it is important that we actually capture the nature of the population, which is why we have to triangulate many different pieces of data in order to put it together to make something that's actually credible. You asked about models, and if there are models of what works in the UK may not work here. So two answers to that. One is there's not that much of a difference in how diseases spread. I mean, we were able to, what happened in China transfer to what happened in Italy, what happened in UK, etc. And the only differences between these different populations was really because of the average age of the population. Italy was struck very hard because the average age is quite high. It's an old aging population. Our Indian population, the average age is 28, Pakistan, the average age is 22, China somewhere larger than that, but Italy is 40 plus, 40, somewhere between 40 and 45. So those impacts will be differential across population. The models may need to be customized, but overall, the nature of disease cannot change, especially for new diseases. This is the COVID-19 or SARS-CoV-2 was a completely novel disease. No human being anywhere had really been exposed to it, apart from maybe people who live very close to a certain set of bats in Hebei province. But you or I or someone in America, all of us started at the same place. This is a big debate about are Indians somehow, do they have some better immunity, it's very dirty, we're constantly exposed to many other things. But overall the answer is probably no. That we all started off at the same place because of the nature of the disease.
Can I make a comment?
So, how can we constitute an error in this model? For example, there's suddenly a big singer sponsored, or there's a flux of tourists coming in. You're guessing the spread of man over this and the interaction. But if there's a sudden flux of tourists to a concert, how are we predicting that?
You can't predict that. I mean, in a sense, that's the modeling choice that you make. If after the tourists come, you suddenly see a rise of cases in that area, then you can infer it must have come from the tourists. And then you can go back and model that. But modeling must always, in a sense, track what is happening in the real world and take input from the real world. I cannot, before the tourists come, I cannot say that, look, I expect on this day, so number of tourists, they, some of them may be infected, they will pass it on. Or I can do it if I have enough information. But often that's not the detail that these models work. They sort of assume some sort of steady state situation, and this is that's what might happen.
And I'm just curious, so for instance, if you look at the fully mixed picture or you put it on a graph, there is some mathematical intuition that you have. For instance, even in case of a graph, you have intuition from the structure of the graph itself. Adjacency, matrix, the Laplacian, they will give you some mathematical intuition. Is there any mathematical intuition that goes into making agent-based models, or is it a lot of trial and error?
In a sense, so the difficulty with, you can write simple agent-based model just like standard Monte Carlo, which is incorporate the fact that two people come together, there's some probability that one infects the other. If one is infected and the other is separate. What's much more difficult is understanding the social and the economic background of agents and how they influence decision making. For that, you do need social data. You need to go out, interview large numbers of people and say, in this situation, what would you do? In this situation, if I change this, what would you do? What would your response be? Where do you get information from? That comes from social data that's much harder to get. So that's why one needs to make assumptions and specify what those assumptions are saying. Within these, we see this. Within this way of describing how agents behave, we see certain types of behavior. Behavior of agents is the hardest thing to model. For example, suppose I have agents who sort of go and come back, etc. But then people begin to hear about some new disease that is coming, something they call COVID, China, something. Every agent says, I'm just going to stay at home until things settle down. My boss doesn't leave me, I'm going to stay, I'm going to cut down my contact with people until I figure out what's going on. That's hard to put in. Who makes that decision, who doesn't, it's very hard to say. Indian population may say, look, I don't care, there are enough diseases around, I will go out, go to my movies and go to my parks, etc. Some other community may not. Again, depending upon whether are you Japanese, are you Indian, are you Chinese, are you African, the way you respond to information, exogenous information, can be very different. And the only way to do that is from various types of surveys, many of which are not done and we don't have information about. So some of this is for future. If you want to put this into the agent, thinking that maybe 5 years down the line, 10 years down the line, you will have this information, and then you can put it into the model. So right now the models allow for it, but don't incorporate it in what they say.
It's more like the management of the disease rather than anything else. Because it's very humocentric, in the sense of considering humans and humans. But disease is a kind of occurs in a physical environment. You might, model some of the social environment through parameters. Again, linking only with the agents, which are agents. I was wondering whether this absence of bringing in the environment, both physical and social environment, which the social environment also cannot be exactly modeled by the parameters of humans. What limitations that would say?
So the physical environment we can do, that depends on the disease that you're considering. If you're considering dengue, for example, you have mosquitoes breeding ground. So wherever you have stagnant water, potentially mosquitoes can breed in there. They can bite the people who are close to it. Other mosquitoes can bite them and then transfer that. So that's one region where you have to know about what is the physical location of water reservoirs, stagnant water reservoirs within the city. In cholera, for example, cholera projects which are waterborne, you need to know what are the connections of the water beams across different regions, the sewage being emitted out into anything near a regular water channel, etc. So that's examples one can put in. If you have enough information about how cities are laid out, you can put this in and say that, look, if someone is a typhoid case here, that must have come from roughly this catchment area. This is where we should look at for other types of cases. Social information, as I said, is difficult. And that's something that in the future, suppose we maybe have a nice model for how Indians in Delhi behave when something happens. They behave very badly in Delhi, but let's say that we know what they will do. And then we can put that into the model. So the idea is to be prepared to assimilate that information right at the outset. But the other thing that you can do is just check different scenarios out. How do people respond to rumors, for example? You can say, okay, let 10% of my population respond to rumors in a particular way, 90% ignore it. What are the consequences of that? What are the consequences of information? Suppose somebody on TV at regular intervals, Amitabh Bachchan or somebody tells you about, please get vaccinated. What is the impact of that? And then I have to constantly benchmark it. If after Amitabh Bachchan is on the TV, I see an increase in vaccination, I can detect a correlation between these two. And I can say maybe this effect will survive for a little bit of time. and therefore expect vaccination to go up and then stay up for a certain time. That would make an implication about social behavior, given information from the outside and how people react to it. But as I said, we don't know. So for much of this, we have to guess how people will behave. As we get more and more social data, we can be more precise about that.
Have you, working with this model, find some critical behavior with the sample results which are unexpected?
There's some things that turn up that's somewhat unexpected. For example, one thing that we did with this model, not just exactly balance or something related, was to say that schools should have opened up long before they actually opened up in India. We said that there's risk to people in general of cases going up into open schools is actually minimal. By then, 30-40% of India had already been infected with COVID-19. Children were not infected because children's schools had been closed and they were at home. But the impact of sending them to school was actually fairly small. So that's one example where policy could have changed based on that, which we made clear during one we spoke about it. And I think in one or two cases, one or two states may have actually made a difference. So the decision we made with presentation for the Kerala government, Maharashtra government, the Andhra Pradesh government, etc. So we were talking to government saying this is the policy we should implement. The other thing that we did was to look at the balance between different types of tests. Should we use an rapid antigen test or a regular PCR test? These were costly. The cost difference was quite substantial in the beginning. So what we said was that the rapid antigen test is equally good provided you test at scale. We evaluated the relative financial impacts of both of these, and we made certain policy suggestions, which again got some press at that time. So my interest is, can we use models to make good policy? Rather than somebody just sitting in a room, 5 people, elderly people thinking, oh, we should do this, we should do that. Here with models, you can actually evaluate what happens if we do it, what happens if we don't do it, what are the financial costs of doing it, what happens if we do this partially or not partially, what happens if we close down schools or don't close down schools, schools and public transport or neither of these, close down offices or not, close down offices in this region versus not don't close down offices at all. With these, with good models, you can actually make out the difference between these options and hopefully make better decisions. That's what.
Can you give an example from COVID? From anywhere in the world where something completely erroneous came out of a model, but it just was completely wrong.
Many of the initial models were not very good, mainly because of choices of parameters were not right. You're trying to reason what is the reproductive ratio of the first 20 or 100 cases. That depends very much on how you detect cases. And our knowledge of how the disease spreads is also very minimal. We didn't realize that you could be asymptomatic for the disease, get transmitted to other people. We didn't realize that you could be vaccinated for the disease. That would reduce your probability of transmitting the disease to somebody if you got it, but not by all that much. So the fact that vaccination would not protect you for the lifetime against subsequent variants was something we didn't know. That depends very much on the biology of the human being. So much of this, you can't really blame the model. It's the fact that the information came in stages to the model. Once they came, they were incorporated, or to change the prediction that you made. And by the time we got to Omicron, the UK National Health Service was producing curves that predicted the next week or 10 days of cases, and they were bang on. We had already improved the quality of our modeling very substantially by the time we get there. Even we said the Omicron should not have much of an impact on the Indian population, based on data that was there from South Africa, which we translated into India. So models depend a lot on the quality of what goes into them. And it depends on and making decisions in a fast-changing, dynamic environment about a completely new virus is very difficult. So, I don't think one could go back and revisit many of these decisions in full hindsight. But it may not be accurate to do that because the sheer difficulties of making policy in a very rapidly evolving space.
So I just wanted to make a comment on that. I did not have the means to do, or the ability to do what Gautam I did, what Bharat said. But, some of us have tried to play with SCIR-like models. And we did it for multiple places in the world. And then, say we did for the US. And then we got down to the state of New York. And then we went to boroughs of New York. And the parameters that we inferred by fitting the data would change. And then we realized by looking at the whatever information we had that it depended very strongly on, say, income distributions. Typical in the for the US you can get those information. So, okay, the density of population, etc., etc., etc. So, the reproductive number, the reproductive ratio for New York would be much larger than, say, for Wyoming. Okay, so but on the other hand, some people try to make policies or whatever, by looking at very sparse data too early in the day without understanding all the pitfalls.
So that's true, but I mean, making policy is always very difficult. We're talking about people's lives and what we should do. We're talking about economies. We're talking about the cost of vaccines, the cost of medication. So it's always very imperfect decision making. So it's our job as scientists to make sure that as much information is available to the policy maker. But it's there, finally, it's the job of the people we elect to make decisions to do this. So why should we elect good people who can actually make the right decisions?
In this pandemic, are the government more disciplined in getting the required data that is required to create your agents? Are we moving the
Very good question. So I think the government is now very much more aware of the need to collect good data to improve surveillance in general. And there's an effort on modeling, the National Disease Modeling Consortium that is based out of IIT Bombay. There are much more tie-ups with international groups to try and look at different areas in India to be of surveillance. But there are some deep structural problems. This is a government that does not like to keep data very close. All government agencies would prefer if you don't look at their data, they want to hold it. And that's very true for health and disease. So that handicaps people. So we have also been saying that look, data that is collected with public money should be made public. If you want to hide it, you have to make a very special case, because the default is to make it public. Then people can analyze it and make different recommendations for policy. I'm not completely sure that we would not have another COVID-19 in the future. We would respond to it as well. But let's be hopeful. Some of these lessons have been learned.
Okay, it's just an observation, like you say the policy decision is taken on the data that you're producing. You take the policy decision, I remember there was a lockdown, and after that everyone was rushing home by train, and there was a lot of crowding at every place. So your model suddenly go haywire because this is not what you predicted. You predicted, made a policy of long-term thinking that everyone will be confined to their places. Now, how do you go about it?
So the idea behind lockdown is that what you don't want is that the number of cases to rise so fast and so high that all your hospitals are filled, you run out of oxygen cylinders, and people begin to die. They may not die because of COVID-19, they die because they don't have an oxygen cylinder. It's a different question. If you've given them an oxygen cylinder, they would have survived. That's what we want to try to avoid. And that's why the long lockdown was essentially there. Can we get a vaccine in place? Can we set up makeshift hospitals? Can we distribute medical facilities across the country? We failed on that count. And especially we failed during the Delta wave, which some of you may remember that we ran out of oxygen cylinders, we ran out of hospital space, people were just doing anything, people were taking money out of common people. That's a failure, that's a policy failure. Could it have been anticipated? Maybe some decisions could have been taken earlier rather than later. I don't think government understood the magnitude of what was happening in the Delta wave until it was too late for them to do anything. Hopefully that will not happen again.
I think because one then deals with such issues like infectious diseases, which are more of social concepts in the sense which affects people, it's very important that how they are communicated to people is going to lead to the success of the model. In the sense, for example, since everybody is talking about COVID-19, you go back to how information was disseminated, how it was given to people, was not the way any kind of scientific information should be given to. Not should be given to people. Like, one should accept that these are very early days. We are working on something which is new. We are ourselves not very sure of what is going to happen. So should we wear a mask? Should we not wear a mask? We are also unsure about it, right? But this is not how things were probably told to people. People were, so that's probably what backfires in most of such social circumstances, is that people stop believing on the information that you give because the information is not given with maybe a caveat or things like that. Okay, this is something new. This is something scientists also don't understand. That
And this is something that really concerns people who work in public health. How do you ensure that the right, how to communicate information, how do you communicate risk, how do you communicate uncertainty?
Yes.
Something that worries people a lot.
Yes.
But also nowadays, compared to 20, 30 years, 50 years earlier, there's also active misinformation.
Yes.
People who send wrong things on WhatsApp groups saying that you do this, you without honey, you do something else, the disease is miraculously done. All these questions are, they're non-scientific.
Yes.
But it's our duty to sort of not propagate them and to tell people who propagate them that look, this is just simply incorrect. So we, as scientists, we try to do that. I was one of the scientists who did that, no doubt many of you were. But that's again where scientists should raise their voices and say, this is what we say for science. It does not have to do with political parties because science does not care which political party you belong to. But we should make sure that the information we communicate is the right bit of information. And we should work as much on communication as we do on the mathematics of the computer communication.
Yes.
So should we also model, you talked about it can be used to spread like on the rumors, that how rumors are spread. Should we also inculcate in public health this same model, like the rumors spread, how people respond? Like there's a shame if I'm having COVID, I will not tell anyone, and that can be harmful because if I'm not sharing I have COVID, I'm coming to campus, I'm interacting with my friends, I'm coming to public transport, I don't know anyone. So the spike will be too early.
You can do that.
Yeah.
You can do people who deliberately conceal these, for example, people who are infected. You can say 80% of people are infected and are coughing will wear masks, or symptomatic will wear masks, but 20% of them will not. What will the impact of that 20%? If I make 80, 90, can that slow down to 60? With agent-based models, you can do all that because you can really make micro-level changes in how the agents respond.
Refuse to get vaccinated.
People who refuse to get vaccinated, that's another example. What happens to them? That's
Like
right.
super spreader and
Super spreaders are a bit harder to do because again, data is not there of who is a super spreader, who is what makes for a super spreader, we don't know.
And
We
if we like
believe that they are there, but we have no generally this agent versus this agent might be super spreader.
if we include that data in the like model, and we can
Can we have
Sorry.
an answer before we have?
Yeah.
Sorry, you can explain, right?
You can say thank you.
Okay, just please,
Now I would like to invite Venksha, President of Physics Society, to deliver the vote.
Hey everyone, I won't take a lot of your time. I'm honored to express my deepest gratitude to everyone involved in making the 29th edition of R.K. Popli Memorial Lecture Series a resounding success. We are deeply grateful to our principal, ROS, the staff advisor, for providing us the opportunity to conduct this prestigious event smoothly. Our heartfelt thanks to Professor Gautam I for sharing his invaluable experience and expertise and providing us with this enriching experience. We appreciate the guidance and support of Dr. Harish Kumar Yadav, our staff advisor, for his guidance throughout this journey. We extend our gratitude to HOD Dr. Sangeeta Sachdeva, professors from the department, Dr. Deboi Jyoti and Dr. Ananya Vajpayee for their presence and encouragement. I would like to acknowledge the tireless efforts of my council members, without whom this success wouldn't have been possible. Special appreciation to our three energetic MCs for their exceptional event management. Huge shout out to the Photography Society and Abir for covering this event. And lastly, we appreciate each one of you gathered here and who has joined us online. And thank you for making this a great success. Thank you
As a token of appreciation, I would like to invite our head of department, Sangeeta ma'am, to present a memento to our esteemed speaker.
Hello everyone. I think everybody, wrote their thanks. Only Venetia has left this entire thing. The president of the Physics Society. So these are the people, actually, the Physics Society, the council members, actually, who did all the works. We did a very little work, basically, here, but they exaggerated my guidance and all those things. But, that's really hard. I really thank my colleague actually for giving me the guidance to select the speaker for this 29th Popli lecture series. I thank especially him. I thank especially the professor from the university here. I thank everyone present here for this series. This is a successful completion of the 29th annual Popli lecture series. Thank you all. Please, the staff advise the council members basically can please come up in front so that everybody will see. Please just come in front momentarily. Come on. Venetia, the president of the Physics Society, please come forward quickly. Come inside, come inside.
Come on. They're not sure how much work each one of them did, so they are a little doubtful about their coming to the front, right?
You're a big council. Okay, introduce yourself. Start.
I'm Adishri, I'm the Associate Secretary.
I'm Kedar Matthew.
I am Abhishek Singh. I'm the fineman head.
I am Jasmine. I'm the journal.
I am Kavya Tiwari, General Secretary.
I'm Physics Yadav, I'm the staff advisor.
I'm Ravisha, the president of the society.
Hello everyone, I'm Devarshi. I'm the vice president.
Hello everyone, I'm Adit. I'm the treasurer.
Hello, I am Jatin Yadav, extended council.
I am Sona, I am also extended.
I am Dhruv. I am the general executive of.
Hello, I am Shlomo. I am the extended council. Hello, I am Nitish. I am the extended council. Hello, I am external
Also, we have Tanya with the speaker.
Kanya, she is the technical head, and also Abhir, he is also the part of the council.
Thank you. Thank you again, Professor for accepting our invite and come here and to all of you. Thank you.
I request everyone to gather outside for a group picture and then we can have our
Also, students who are not filled the attendance sheet, please kindly fill the attendance sheet. Please, can you all please sit down?